Hey there, Iron Designer here again. So I just wanted to bring you a new video using the Tyler Hicks Standard Handbook of Engineering Calculations 3rd edition. We're going to look at a problem solving here, doing bolt clamping analysis with a check on endurance for the bolts if they are not in a static state, which typically in a flange setup situation where you've got pressure buildup and reduction, then that's considered dynamic because the pressure is going to zero back to pressure, and this cycling is considered endurance. So if you have this book, I think the problem is on page 116 through 119, and this video is for educational purposes only. And this procedure given here can be used to analyze bolted joints used in pressure vessels in many different applications such as power plants, hydraulic systems, aircraft, marine equipment, structures, and piping systems. The new thread forms permit longer fatigue life for bolted joints. For this reason, the bolted joint is becoming more popular than ever. Further, electronic bolt tightening equipment allows a bolt to be tightened precisely up to its yield point safely. This gets the most out of the particular bolt, resulting in product and assembly cost savings. The key to economical bolted joints is finding the minimum bolt size and clamping force to provide the needed seal. Further, the bolt size chosen and clamping force used must be correct, but some designers avoid the computations for these factors because they involve bolt loading, elasticity of the bolt and the joint, reduction in preload resulting from embedding of the bolt, and the method used to tighten the bolt. The procedure given here, developed by G.H. Hunker, a consultant with Unbraco SPS European Division, simplifies the computation. Data given here were presented in Product Engineering Magazine, edited by Frank Eppel, mechanical engineer, Masters in Engineering. So I just wanted to remind everybody about the other videos on the Iron Designer channel. Just wanted to go over that really quick. We've got How Weldments Fail. That's a very good video. Working with Lincoln Arc Welding textbook. How Bolt Patterns Fail. Per chart analysis, web scraping. I've got videos on CSV and SQL, calculations on centrifugal energy, kinetics, number analysis, mechanical engineering stress and kinetic energy analysis, learning to interview, reverse engineering, numerical analysis, safety designs, starting your business, all the way on through to robotics and smart machines. So the very first thing you want to do is look at the cross section of your design, and this is part of the problem here. It just shows a closed flange on the end of a pipe. What I'm showing here is just basically just to show you what it would look like in a 3D model. It just has 8 bolts, and even though this one is open, but just imagine that it was closed like a cap, just like this. So the problem we're going to analyze right now is a flange with 8 bolts going through. This is the cross section. These are the dimensions. And what we're going to do is look and see that they're giving us the internal diameter of the cylinder. Shows you here 5 inches. Is shown 5 inches. The axially pressurized area of the cylinder head, you know how to calculate the area. It's this formula, and you get this value, 19.63 inches. And what I do typically is I'll run in parallel like a data sheet calculation. If you've seen my videos in the past, you know that I focus in on Microsoft Excel to do 90% of my calculations. I never try to do it by hand unless I'm trying to understand something, but then I'll put it into Excel because you can play what if a lot easier in Excel, and you can quickly change values. Say I change this to 5.5, you know, you see the number changes the pressure head area. When I go back to 5, it's the same value as was shown in part 1. So we're going to jump back and forth between the screens so we can make sure that what Tyler Hicks did is actually coming out with the correct value. So we're going to jump to data sheets and then back to the calculation back and forth. At the end, I summarize it all up in a final setup. And again, it's just this is where I'm going to play the what if. And if I need to print this out for someone, it's formatted so they could visually see it as a printout. So that's why I kind of duplicate my work, because as an engineer, you need to communicate with other engineers or your client, your customer, or your manager. So part 1 is done, and we have verified the value. So in this part of the calculation, we're going to find the applied working load on each bolt. And this is critical in order to make the connection sustain the load. So since the 8 bolts are specified for this flange joint, each bolt will carry 1/8 of the total load found from FA, from the force on the area. And that's defined as the pressure times the area divided by 8, where FA is the axial applied working load in pounds, and P is the maximum pressure in the vessel in pounds per square inch, and A is the axially pressurized area in inches squared. Or you could also say that FA, when you plug the numbers in, is 3,250, which they're giving you that pressure, it's a given, times the area, which we computed in part 1, divided by 8. So now we have the pounds axial force per bolt. They're just rounding it up to 8,000 pounds for the calculation purposes. So I just also wanted to say, if you like these videos and they have good content for you, if you could please give me a like and a comment and a share and subscribe to the channel. It helps the channel grow, and it gives me incentive to make more videos along this same topic. It seems to be a very popular topic on my channel, is bolt analysis and bolt stress. So I'm going to continue doing these every now and then, but I'm going to mix it up with some other machine design and other engineering related topics as well. So here we are in the third part of the computation involving computing the bolt load produced by torquing. So now we know what the axial load is on the bolt, and now we need to compute the load on the bolt from torquing the bolt. So in this case, we're going to assemble our connection using a power wrench that uses air to tighten the bolt nut. And in the worst case, the tightening factor using an air wrench could go up to 2.5 if the bolt is torqued all the way to the yield limit, as it said in the previous slide. So here it says an air stall power wrench will be used to tighten or torque the nuts on these bolts. Such a wrench has a torque tightening factor CT of 2.5 maximum as shown in table 65. Using CT equals 2.5, we find the load on each bolt PY in pounds, causing a yield stress is PY equals to CT times FA. And if you remember from the previous data, so we're just going to multiply the 2.5 times the 8,000 and we'll get 20,000 pounds. And that's the bolt load produced by torquing the bolt with the air stall power wrench. So now we're in part 4 of the calculation, and I just want to show you that in the data sheet what I did is these numbers here, they correspond to the numbers in the question. So as I'm going down, part 3 is being calculated here. You see the 20,000 pounds and the 2.5 from the CR, the CT value in the table. And now we're here in question 4. And so you see I have the 4s here. It talks about the yield ratio and the expected yield strength. So we'll go back to part 4. So find the ultimate tensile strength PU for the bolt. With the yield strength typically equal to 80% of the ultimate tensile strength of the bolt, then the PU is equal to PY divided by 0.8, which is equal to 20,000 divided by 0.8, which is equal now to 25,000 pounds. Now here in section 5, we determine the required bolt area and the diameter. So we're going to select a grade 8 bolt having an ultimate strength of 150,000 pounds per inch squared. The nominal bolt area must then be AB equal to PU divided by U, which is equal to 25,000 divided by 150,000, which is equal to 0.1667 inch squared. And that from a table, when we calculate the diameter, we get dB equals 4AB divided by pi, all raised to the square root. We get a diameter of 0.4607 inch. So we have to raise that up. The closest standard bolt size would be 0.5. And you choose a 1/2 13 UNC bolt, keeping in mind that the coarse thread bolts generally have stronger threads. Some debate that fine thread is stronger or coarse thread, but we're going to go with this because we're going to have a data table to take a look at this data values. And back over here in the data sheets, that's exactly what I've done here in this section right here. You have the bolt grade is 8, the bolt strength is 150,000 psi, the nominal bolt area, and all this is computed. You can see the values are computed. And then I compute this value, which is the theoretical bolt diameter. You can see the formula is computed here. And then here I use the in Excel ceiling in order to raise up this to the next highest value within every 0.5 increment. And then the bolt selected, I manually input that because it's in the table. And the table, you can see I have copied a table here that you could find these all over the internet. But for now, you have the 1/2 inch bolt, and you don't use the BSW, that's the British. So we have to go across to here, the uniform American sizes. So you have half 13 UNC, and it gives you other metric data. But when you go back to this, you'll see in the past they just said NC, but the data is the same. Now, what we want to do is find the spring rate of the bolt that we've selected. So the general equation for the spring rate, K, is pounds per inch, okay, is the spring rate. For a part under tension loading, it is K equals AE, and divide by, I chopped it off here, there's an L, so AE over L, where A is the part cross-sectional area in inches squared, E is the Young's modulus. In this case, we're going to use 30 million pounds per inch squared. L is the length of the section in inches. And we're going to find the spring rate of a part with different cross-sectional areas as a bolt has. And we're going to add the reciprocal of the spring rate of each section, or 1 over K total is equal to 1 over K1 plus 1 over K2, and so on, until all the different cross sections are included in the overall total reciprocal of the spring rate. For a bolt which consists of 3 parts, the head, the unthreaded portion, and the nut, the spring rate determined by Juncker, a consultant with Umbraco, is given as 1 over KB, which is equal to 1 over E, the Young's modulus, times 0.4 D over A1 plus L1 divided by A1 plus LT divided by AM plus 0.4 dm divided by am, where d is nominal bolt diameter in inches, a1 is the cross-sectional area of unthreaded portion of the bolt in inches squared, am is the cross-sectional area inches squared of the minor threaded diameter, dm, L1 equals the length of unthreaded portion. In our case, it's 0.75 for this bolt. L is the length of threaded portion being clamped in inches. The values of 0.4D and 0.4dm pertain to the elastic deformation in the head and the nut areas respectively, and were derived in tests in Germany. For a 0.5 inch diameter bolt, the cross-sectional area A1 of the unthreaded portion of the body is A1 equals pi times 0.5 squared divided by 4 is 0.1964 inches squared. The minor thread diameter of the half 13 threaded bolt is from a table of thread dimensions, the 0.4056. Thus, AM equals pi times the minor diameter squared divided by 4 equals 0.1292 inches squared. Substituting the appropriate values in the spring rate equation for the bolt gives 1 over KB equals 1 divided by Young's modulus times these values again, all being plugged in. There you can see them all being plugged in. The resulting KB, when you take the reciprocal, is about 1.9 million pounds per inch. And when you look at my data sheet for section 6, then I've plugged in all the values, and I did the work on the side here. So these are the components of the calculation, and then I sum them up according to the formula for the reciprocal of the spring rate of the bolt for the multiple components and the parts of the bolt. And when I take the value of KB, you have here exactly 1.893 million pounds per inch, exactly like in the example. So we're now in part 7. It's also a bit lengthy, but it's not that complicated. What you're going to do here is compute the spring rate of the joint. So first we did the spring rate of the bolt, and now we're going to look at the spring rate of the joint. And basically what they're saying at Unbreako, and I can read it to you, the calculations of the spring rate of the joint can be simplified by assuming that the bolt head and the nut, when compressed the joint as the bolt is tightened, will cause a stress distribution in the shape of a hollow cylinder, with most of the joint compression occurring in the vicinity under the bolt head and the nut. So what they're saying is, if we go back to part 1, that when the bolt tightens up on the flanges, that this is creating a cylinder of force all the way through. And I've seen other textbooks where they say it actually creates a cone underneath here, and this is like an inverted cone going up. So in this case, in the research that they did in Germany, they found that that it's not a cone, although other research shows it is a cone, that it's a cylinder acting directly through and parallel to the body of the bolt. Okay? So to calculate an equivalent area for the joint AJ in inches squared for use in the spring rate equation for the joint, the designer has a choice of one of 3 equations. Case 1 is when most of the outside diameter of the joint is equal to or smaller than the bolt head diameter, as when parts of a bushing are clamped. So that's case 1. That's not our situation, but I went through and did this calculation anyway. Case 2 is when the outer diameter of the joint DJ is in greater than an effective bolt head diameter or washer DW inches, but less than 3 times the diameter of the head of the bolt. So you have DW in inches, but it's less than 3 times DH when AJ equals this equation here. And I did compute this equation in the spreadsheet. I'll show it to you in the data sheet. And then finally, case 3, when the joint diameter DJ in inches is equal to or greater than 3DH. And I calculated that as well. So the formulas are slightly different, but I calculated all 3 scenarios. And for this bolted joint, case 2 applies. Assuming that the bearing diameter of the head or nut is 0.75, then AJ is this formula, and we'll get into that in a minute. So here we are back in the data sheet tab, and I just wanted to go down and show you the calculations for the cases that I did. And what's happening is you're getting these different areas, and I think what the author wants you to find is the smallest one. So if you're looking at the entire joint, you get 94.83 inches squared, which is very large and definitely not something you're interested in. If you look at case 2, which is what they recommend, with an outside diameter of the joint along the center line of the bolt pattern. See, the center line of the bolt pattern is 9. If you look at the total outside of the entire joint, it's 11. So when you look at my calculation, that's where this 11 is coming from, and that's where this 9 is coming from. And when you do the case 2 calculations, you get the smallest area of the joint. Remember, they were talking about a cylindrical pattern where the force is in parallel through the joint through a cylinder created by the bolt. And then, of course, case 3 has a larger area of the joint, AJ. And so that's why I'm not using that value. I'm using this value. I believe the author wants the smallest value to be used. And off here to the side is where I have the computations of the different portions of the calculation. So in 7, there's like this portion and then a middle calculation and then this last calculation. So then I assembled it all according to the way the formula is. And then here you can see the result is 0.4692, and in my data sheet it's here 0.46921. Okay, so I always show you all my numbers and where they come from. And they say inserting this value of AJ in the spring rate equation of step 6 gives the KJ value with this formula of 7.003 million pounds per inch. And in the data sheet, that's what you have, 7.003 million pounds per inch KJ. In section 8, we're going to find the portion of the working load that unloads the clamp joint. So remember, the author said that sometimes the bolt head will embed itself into the flange, and this embedding is allowing the bolt to stretch. And they're saying that in their tests in Germany that it's about 10% of the joint connection is due to embedding and compression. So they're saying the loading constant CL considers the bolt and joint elasticity and is given by CL equals KB, which we computed previously, times KB plus KJ, which we computed previously. For this joint, CL is, they divided the numbers by 1,000. So remember, this used to be 1.8 million, 7.03 million. They just divided by 1,000 to make the calculation easier. It's still proportionally the same. And they get a value 0.2128. So then the FP, the portion of the working load FA that unloads the clamp joint, is FP times FA, 1 minus CL, which is 8,000. If you remember, that was the upgraded value from the bolt forces, times 1 minus this loading constant, 21.28 or 0.2128 equals 6,298 pounds. So now the clamp joint is not clamped to the full 8,000, it's clamped to this 6,300 value here. And in my data sheet section 8, that's exactly what we get. We have the loading constant computed by formula. We have the original KB. We have the new values that are reduced by 1,000. And we're computing the unloaded force. So it's really, what they mean is this is the force minus the take up from the embed. And this is the remainder of the clamp force load. So I did kind of give you a look ahead here in part 9. Determine the loss of clamping force due to the embedding. Some embedding occurs after a bolt is tightened at its assembly. A recommended value is 10%, or specific values can be obtained from the test. Thus, the loss of clamp force Fz in pounds is equal to 0.1 times Fa, which is about 800 pounds of clamping force embedment. And in my data sheet in section 9, that's what I've computed here. Just based on their recommendation, I just plugged in the value and multiplied it times the original clamp force without the clamp reduction, without the unloading force. So in section 10, we're going to find the clamping force required for the joint. And since the working load in the vessel fluctuates from 0 to 8,000 pounds, the minimum required clamping force, the minimum would be 0 at a fluctuating force of 0. But now the maximum required clamping force Fm in pounds can be found from the formula Fm equals to Ct times Fp plus Fk plus Fz, since all the variables are known, or we could plug in the values that Fm is equal to 2.5 times 6298, that was the force reduction on the clamp, plus 0, which would be the Fk, the starting pressure force, plus 800, which is the embedment unloading load. And you get there 17,745 pounds. Since the bolt has a yield strength Py of 20,000 pounds, it has sufficient strength for static loading. But for dynamic loading, however, the additional loading is Fs, which is equal to Fa times Cl, where Fs is the portion of working load that additionally loads the bolt in pounds, or that Fs equals 8,000 times the 0.2128, which is equal to 1702 pounds. So as you can see in my data sheet, I've accounted for those calculations from section 10, and there's the value that they're calling the dynamic force of 1702 pounds. Next, we're going to look at the endurance limit, and we're going to determine that the bolt we originally selected from the upsizing from the area calculations is insufficient to withstand the load of endurance and the fluctuating pressure. So here, in checking the endurance limit of the selected bolt, the endurance limit SE in pounds should not be exceeded for long life operation of the joint. Exact values of SE can be obtained from the bolt manufacturer or computed from standard endurance limit equations. For grade 8 bolts, SE is equal to 4600 times D raised to the 1.59 value, or that SE equals 4600 times 0.5 raised to the 1.59, which is 1,527 pounds. The value for Fs that was computed for the half-inch bolt is actually 1,702 and should not exceed the 1,527. And since it did exceed that value, a bolt with a larger diameter must now be selected. And we're going to check into the 5/8 bolt instead of the half-inch bolt, and we find that the endurance limit becomes SC equals 4600 times 0.625 raised to the 1.59, which is 2,179 pounds. And in my calculation on the side, I get 2,178.7. It's pretty close enough to 2179 pounds. So the new bolt size should definitely be the 5/8 bolt. Thus, although the 1/2-inch bolt would have sufficed for static loading, it would not have provided the necessary endurance strength for long life operations. So the 5/8 bolt is going to be selected, and a new clamping force FM now becomes 16,970 pounds, and it's calculated by using the same series of steps detailed above. So in closing, I showed you this table of bolt dimensions, but I wanted to come back and show you this here. This is the summary of the calculations that we did in the data sheet. So that other tab summarizes this tab here. And this is really what you want as an engineer, a professional engineer, so you can print things out. So what you can do here, originally you see this toggle. So originally we had the 1/2-13 bolt, and what you can do here in the toggle, it's like a dashboard. You can do live modifications for your customers on demand, so you can see what the what ifs are, and you can verify that things are changing. So you can see that the original endurance limit for the 1/2-inch bolt was 1,528, and here I put in some if statements that if they're equal to, say, match. If one is less than the other, say upsize, and if it's otherwise it exceeds, then it will exceed, and you are more than capable of doing endurance. So let's see if that works. So here we've got the 1/2-inch bolt in the toggle. We're going to change that to 0.625 for the 5/8, and then we see now that the value says matches. Remember before it said upsize. So this table is like a smart table. It's telling you need to upsize your bolt. When we upsize the bolt in here and change the value to 625, now it says matches. So what it means is that the value of endurance is matching the value of the bolt's endurance limit. What happens if we put in a larger bolt? What happens if we put in a 3/4 inch bolt? So we put in 75 here, and now the table has changed to exceeds, and the value is now 2911, which is far larger than the endurance limit required for the 5/8. So that's some of the things you can do when you're doing your calculations as a professional engineer. And I hope you enjoyed this video, and I'll be uploading a video very soon. Thanks.